we are pleased to present you a report on the topic. Deflections of a slab on an elastic base when it is weakened. Authors: Alexander Kolesnikov and Andrey Ivanov. Modern foundations in the form of solid monolithic slabs are used for relatively weak, water-saturated soils and significant loads on the foundation. During operation, a partial deterioration in the bearing capacity of the foundation soil under a building or structure may occur, which entails the destruction of higher structures even when using a solid foundation. These negative processes can be taken into account at the design stage by introducing additional coefficients or calculating additional impacts. This will invariably lead to an increase in the cost of the structure and an increase in its weight. Therefore, the introduction of any additional coefficients must be carefully justified. A slab on an elastic foundation can be described by a system of equations 1, where E, elastic module, H shell thickness, phi effort function, W deflection function, Z function loading on slab, K modulus of elastic foundation reaction, T, soil shear parameter. Modulus of elastic foundation reaction and soil shear parameter can be described by an equations 2 and 3, where N nu, elastic module and Poisson's ratio of the soil, depth of the soil stratum, psi, Z, function of cross-distribution displacements. Function of cross-distribution displacements can be described by an equation 5. The stress-strain state of a structure is determined primarily by the values of stress and displacement. Equivalent stresses in the slab on elastic foundation are found by the fourth stress hypothesis. Stress coefficient can be described by the equation 6, where nu, Poisson's ratio, A, B, unknown of Bubnov-Galerkin method, Zx, Zy beam function. The deflection of any points of the slab on an elastic foundation can be obtained using the expression 11, where Zx, Zy are the Vlasov's beam functions. The quantities Ma, Mb are constant coefficients representing the ratio of the support moments of a simply supported beam loaded with intensity Q to the support moments of a beam rigidly clamped on both sides of the same load. The coefficient gamma can be represented as a function that specifies the different rate of attenuation of sediment under the base of the foundation. For example, the function could be used the equation 14. Where min is the minimum value of the coefficient characterizing the rate of attenuation of sediment in the depths of the base under the base of the foundation, S, M, L, and eta, theta coefficients characterizing the shape of the change in the coefficient characterizing the rate of attenuation of sediment in the depths of the base under the base of the foundation. Expressions for determining deflections 11 and stresses 6 allow one to study the stress-strain state of slabs on an elastic foundation with an arbitrary change in its characteristics. Let us consider the change in slab deflections with a decrease in the strength characteristics of the soil under a part of the structure. To check, let's set some values. Consider a reinforced concrete slab 40 cm thick, with plan dimensions of 12 by 8 meter, loaded with a uniformly distributed load of 55 kN divided by meter squared. The results of determining the slab deflections, derived using expression 12, are given in Table 1. The results of deflections derived in a software package based on the finite element method are also presented here. Since the slab was loaded with a uniform load and the characteristics of the base are constant, we obtain only vertical displacements. Let us conduct research into changes in the stress-strain state of the slab when the properties of the elastic state change. Let us determine how displacements change in the absence of a base under part of the slab. We will sequentially remove part of the base under the slab in the following sequence: 1/12, 1/6, 1/4, 1/3 of the larger size of the slab in plan. From figure 3 it can be seen that when the weakening exceeds more than 1/4 of the larger dimension in plan, the opposite edge of the slab is torn off. Let's find a more accurate value for the maximum absence of a base under the slab without tearing off the opposite edge of the slab. To do this, we will investigate the change in shell deflections using expression 11. Here the characteristics of the soil will be specified using function 14. We simulate a deflection as the size increases in the plane for a slab with given dimensions using expression 11. From figure 5 it can be seen that the results obtained using expression 11 are similar to those obtained using a software package based on the finite element method. If there is no base more than 1/4 larger in plan size, the opposite edge of the slab is torn off. Let us plot the dependence of the deflection of the edge of the slab, opposite to that under which the base is weakened, on the parameter n, which is included in expression 14 and affects the fraction of base weakening. From figure 6 it can be seen that the separation of the edge of the slab opposite to the one under which the base is weakened occurs at a parameter value of n equals 3, 6. This corresponds to 0, 6b, larger in plan size. The expression for specifying the properties of the foundation 14 allows you to model a more flexible change in the bearing capacity of the soil under the slab and obtain accurate values of deflections 11 and stresses 6. The work considers slabs on an elastic foundation. The proposed formulation of the problem can be used to analyze the deflections of the slab and the stresses that arise in its middle surface when the bearing capacity of part of the foundation soil changes. A comparison of the results of slab deflections obtained using analytical expressions with a software package based on the finite element method shows good convergence of the results. The presented expression, which can be used to specify changes in the distribution of load-bearing properties of the foundation, contains several parameters that provide ample opportunities for modeling its operation. The presented graphs of changes in deflections at various points of the slab show wide possibilities for accurately determining deflections and stresses in a slab on an elastic base in the absence of it under part of the slab or in the reduction of its strength characteristics under part of the slab. Thanks for your attention.